Hello, scientists. We are going to talk about light in Unit 8. Let's talk about the electromagnetic spectrum to start out with. Light is just one part, visible light is one part of the electromagnetic spectrum here. We've also studied about other types of waves, like infrared waves when we talked about heat. That's how heat and energy can travel without needing a medium. Visible light doesn't need a medium either. It's not a mechanical wave, it's electromagnetic. X-ray and gamma rays are something we may have already talked about in first semester or second semester, if you've taken that first. And the scale here is about the scale of the wavelength here. Radio waves are very large, long waves. They have a long wavelength, the size of buildings. Microwaves have the size of, maybe a butterfly, a couple of centimeters. Infrared waves are pretty tiny. They're the size of a needlepoint. And visible light gets very tiny. That's down to nanometers as a wavelength. In fact, we talk about nanometers here. Like 400 nanometers is kind of a purplish light, where 700 nanometers is a reddish light. So the color of the light depends on the wavelength. Purple is the shortest and red is the longest. The sun is the primary source of light on Earth. You might think it's the fluorescent lights that might be over your head right now, but honestly, as far as all living creatures are concerned, it's the sun. We usually see sun as white light, which is a combination of all light colors. When you combine all the light colors, you get white. And the opposite happens when we talk about pigments, and we'll talk about that in a minute. When we see sunlight that is separated into colors, we see a rainbow. You can see right here that that white sunlight is separated out into the colors, and here's how this happens. The light is reflected off inside the raindrops, and as it's reflected, it's traveling at different speeds and different frequencies because it has different wavelengths. And as it travels through the raindrop, those wavelengths are kind of separated out because of the different speeds. Some of them are slowing down more than others. And you can see that color separate out because of the reflection and because of the refraction. Refraction is change in speed because of a change in medium. This is reflection and refraction in a water droplet. We'll talk about more about reflection and refraction in just a moment. This is reflection and refraction in a prism. Refraction is the bending of light, and that's what causes the separation. Reflection is just a bounce. Light behaves like other waves because it can be reflected and refracted like sound or water waves. Here's a water wave being refracted or bent because it's going into a shallower area. So water waves change as the depth changes and they are refracted. As the medium or the depth of the medium changes, the wave is bent or refracted. So refracted means bent. Sound waves can be reflected, and you know that as an echo. If you've ever yelled into kind of a rocky place that doesn't have much vegetation and heard an echo, or maybe even in your house there's a bit of an echo, you have heard sound reflected, just like light can be reflected. Light behaves like a particle and a wave, and that happens when an electron falls down in an energy level. We know from studying atoms there are different energy levels represented by circles here. And when an electron travels from a higher energy level to a lower energy level, a light particle is emitted. That's a photon right here. You can see this represents the electron. It's going down a level, and because of that loss of energy, some energy is emitted as a photon. Photons are created when electrons change energy levels. This is important. It's on your test. Remember this. Photons are created when electrons change energy levels. When an electron goes down an energy level, some of the potential energy is converted to light and emitted as a photon. Now, the color of that light, or the amount of energy in that photon, is determined by how far this electron falls. This amount of energy here between the two energy levels in the atom determines the amount of energy in this photon and the color of the photon. It has a specific wavelength or a color if it's invisible light, and it's called a photon. It's a discrete packet of energy. So what's a photon? A light behaving like a wave, light bending, light reflecting, light changing speed, light behaving like a particle. And if you guessed E, you're correct. Light behaving like a wave is refraction and reflection. Light bending is refraction. Light reflecting is reflection, of course. Light changing speed is what happens in refraction, but light behaving like a particle is indeed a photon. Laser light is created by using photons that all have the same wavelength. That's why lasers have the same color. The material photons come from determines the wavelength or the color of the light. You can see that there are different colors here. Green has a wavelength associated with it in nanometers. Blue has a wavelength associated with it in nanometers, and this red laser pointer here has a different wavelength associated in nanometers. This laser is using argon gas to produce blue light. If you have a ruby laser, you get red light, with a different nanometers, of course, than the blue light. Why is laser light, at least in the same laser pointer, laser, all the same color? Is it the same amplitude, the same magnitude, the same wavelength? All the light comes from the gas, or all the light is white light? Take a guess. If you guess that all the light has the same wavelength because it's coming from the same kind of material in the same laser, like for example this green laser, it all has the same wavelength. What's the reflection of light? Well, let's go take a look at what light reflection looks like. Reflection, let's tell a little story here. We've got our Star Wars good guys here, and we've got our Star Wars bad guys over here. And Luke has his wonderful lightsaber here, but his lightsaber, because Luke has been shrunk to Lego size, is too big for him to pick up. So he has to figure out a way to still get Darth Vader over there with his lightsaber. So fortunately, Luke has found a mirror here, a very large mirror, that he can use to reflect the light. And let's turn off the light so we can check this out a little bit. You can see that the laser is pointing at the mirror, and if we point it at the mirror, it's going to go over and at the bad guys. And if you notice, the angle of incidence equals the angle of reflection, and I'll explain what that means in a second here. The angle which it hits the light, hits the mirror, is the angle that it comes off the mirror. And if we move it around, you can see that that angle changes. So reflection is basically the idea that you bounce light off a mirror. And it's really easy to see here because it's a single beam of light from a laser, and it basically makes a nice line. And this is actually what happens to all the light. When you look in the mirror, you can think of it as lots of single beams of light here that let you see yourself in the mirror. And let us get Darth Vader here. Let Luke get Darth Vader. To illustrate how light can be refracted, I have a jar full of two different mediums here. I have actually three. I have some coconut oil, which is kind of on top of the oily layer here. I have some olive oil kind of in the middle here, and then I have some water with a little bit of milk added to it so you can see the laser beam better inside the water. So as light changes through the different mediums, the laser pointer beam is going to bend just a little bit. As you can see, the laser pointer comes down through the oil here, and then it kind of, you see a lot of glowy because the light is scattered on the milk particles. But you can see right here at this layer here, the light bends a little bit because it's changing speeds as it changes media from oil, these two different kinds of oil, to the water. So that's refraction, the bending of light. And you can see it through the glass here. It looks even more bent because you're seeing the light bend through the glass as well. So this bending here, the bending of light as it changes speed, as it changes media, is refraction. Refraction is bending. Also see how light is refracted through a prism. You might have something like this as a sun catcher in your window. It might throw, as sunlight goes through it, white sunlight goes through something like this. You might get sparkly rainbows on the floor of your kitchen or wherever else you have it hanging. And as you can see, the laser here doesn't come out quite at the same angle that it went in. Here it's coming out, and it's coming in that way. Let's shut off the light so you can see it a little bit better. You can see that the laser light is bent. Normally you'd expect it to come out about over here, but it's really coming out over here. You can see where my finger is. This is where I would expect it to come out based on the angle just looking at the laser. But because it's going through a different media, it's bent a little bit, slows down when it hits the glass, and is bent. If I put it in on the end, it's also reflected within the prism, as the end of the prism is frosted to reflect light, and you see reflection and refraction in the same piece of glass. It's reflected internally and the whole thing glows green. I can show you the end here. You can see how the end is frosted. It's treated with a chemical to make it not smooth, and that reflects the light inside the prism. So now we've talked a little bit more about reflection, the bouncing of light, and refraction, the bending of light. Which one of these pictures do you think is reflection? Which one is the bouncing? If you guessed this one, where it's reflecting like off a mirror and it's light bouncing back, you're absolutely correct. Laser light's also a good way to demonstrate refraction, and we talked about that a little bit, how when it changes mediums from air to water, the light bends, it changes speed, so it looks bent. When it enters a different substance, it slows down. In this case, this photo is water. So the light is going from air to water, and it's slowing down, and then of course here it's reflected. The change in speed makes the light look bent. After it passes through the medium, the light returns to its previous speed. So if it goes through window glass, there would be a light ray, it would be moving fast, it would slow down a little bit for glass, it's still moving quite quickly, and then it would move faster again once it passed through the glass. Refraction is why things look bent when you're viewing through a glass of water. It's because light is changing speed and the light bends. What causes light to bend? Here's a good picture of light bending or refracting. See if you can remember. Is it change in direction, distance, work, speed, or wavelength? If you guessed speed, you're absolutely correct. When it passes through water, here's a clue. Here's some raindrops looking at the Golden Gate Bridge. It's upside down and it looks a different shape. The light waves slow down because they are refracted. Here's some important concepts for this lesson. This isn't all you need to know for the test, but we'll wrap up this part of the review. Visible light is part of the electromagnetic spectrum. White light is a combination of all colors, and light behaves both as a particle and as a wave. And here are some other important concepts. I'll see you in part 2.